So today we're looking at 5.4, solving compound inequalities. A compound inequality has to do with compound statements, and what we really want to do is we want to look at how compound statements are put together and what makes them true or not true. Again, true or not true things is really where all of this solving is. When is our mathematical statement true? Okay, so we're looking at a compound statement, and a compound statement is made up of two simple statements, okay, connected by a word and or. Okay. Before you can determine whether a compound statement is true or false, you must understand the words and or. What do they truly mean, and how do we actually use them to decipher what we're talking about? So the first statement we're going to look at is a spider has 8 legs and a dog has 5 legs. So right away you're probably like, oh, that's clearly false, that a dog doesn't have 5 legs, and it's clearly true that a spider has 8 legs. But for a compound statement connected by the word and to be true, both of these simple statements must be true. And since one of them is clearly false, that makes the whole statement that we're talking about false. So what we see, as you see at the bottom, since one of the statements is false, the compound statement is false. So if one of these compound statements with an and is false, the whole thing is false. That is not the same as an or statement. When you have an or statement, this is what can happen. A spider has 8 legs or a dog has 5 legs. Well, we may not say this normally, and it may sound a little different to us, but really what that's saying is the following. If the compound statement is connected by the word or, if only one of them is true, the entire thing is true. So that's all we really need to concentrate on. If I can get one of these, if I have one of these that are true in my compound statement, then the whole statement is thus true. So the first thing we're going to look at is a compound statement. Okay? Don't be scared. They're nice and easy. It's a compound statement, and you can tell because you have 2 inequality symbols. You have 2 of them. And since you have 2 of them, you know that 2 sets of things are going to happen. Before, we've only had 1 of them. And since we only had 1 of them, we really had to only concentrate on what's happening in one part of the equation. Okay? And so what we're going to do is we're going to look at how we do this type of problem. All right? So the way that we work with this problem is we take one inequality symbol and we do that side. And then on the complete other side, we're going to take that same inequality symbol, the other inequality symbol, and do the other side. Now in this case, notice what happens. You have the same exact thing in between what we're talking about. And when you have something that's in between what you're talking about, this is going to be an and statement. Okay? And what I like to think of these as is these are a prison statement. And you're like, uh-oh, where is he going with this? So these are a prison statement because really what we're talking about is this is one of our boundary pieces on the outside of the prison with barbed wire. And this is one of our boundary pieces on the outside of the prison. And the actual inequality variable portion where you're doing things are on the inside of the prison where the inmates are. So this is an and statement because it's bracketed on both sides by the thing that's trying to keep it in between, not outside. Okay? So that's how you'd recognize an and statement. It could be written as and, but more than likely you're going to have the compound inequality have something in between the 2 inequality signs, and that's an and statement. Think of it as prison. So what we're going to look at is we're going to solve each one of these and then go back to our analogy for prison where we want to keep the thing that we're talking about in between. So we're going to subtract 6 on both sides, and then we're going to get 3x and minus 9 less than or equal to, divide by 3 on both sides. Okay, that's the multiplicative inverse, which would be multiplying by 1/3 or dividing by 3. I get 8 on the left, x on the right, and minus 3 on the left. Okay, so this is one part of this compound inequality. Remember, compound puts together 2 simpler statements. So that's one simple statement. Now I have to look at my other simple statement. So I'm going to solve this one as if it was a completely separate thing. So I divide by both sides by 3, and now I end up with x is less than 2. This is my other simple statement. Okay? And since we're going to graph this solution set, okay, we're going to look at how to graph it. Okay? And that'll actually help us talk about what the solution set looks like when we put it in set builder notation. So before, when we were graphing, we had one boundary number, and then we decided which way our arrow had to go. Now we have two boundary numbers. And so I have a boundary number at -3, and I have a boundary number at +2. Make sure you put them in the correct order on the number line. Now, +2 is kind of like the electric fence that we talked about. You can get close to it, but you can't touch it. It's an open circle. -3, however, is not an electric fence. This definitely goes along with my prison analogy. Okay? So if I really look at this one right here is saying that x is less than 2. Well, we know less than 2 goes that way. And the other statement is also in conjunction as part of the compound, and it's also saying that x is bigger than 3. And so we get to actually see at the end that this and statement that we're talking about is really just the prisoners on the inside. This is where the x value we're talking about lies. This is where the prisoner lies, behind bars. Okay? So what we really want to do is we're going to actually connect these. We're going to say all the values less than 2, but I can't go past -3 because there's an and here. And remember, for our statement, an and, both parts have to be true. Well, the only time this is true is for numbers that are less than 2. The only time this is true is for numbers that are greater than -3. And the only time that can happen at all is between -3 and +2. And so what we end up with looks like a barbell. Okay? And really what we're saying is that x, all the numbers that we can talk about that makes this compound inequality true, must lie between my open circle for 2, that electric fence, and lie between my closed circle for 3, that non-electric fence. So really x is trapped, it's a prisoner, between these two boundaries. One an electric fence that you can't touch, an open circle. One a regular fence, but it probably has some barbed wire on it that you can actually touch. And the x lies in between. So this would be an and statement because we end up with the variable sitting in between the boundaries that we talk about. Well, that allows us to kind of have an easier way to think about how we're going to write our set builder notation. So as always, we have our fancy bracket. We talk about the variable that we've used such that. Now, such that what? Such that the variable that I'm talking about, and I'm going to do this a little backwards, is greater than or equal to -3. This variable is greater than or equal to -3, but also, which means and, less than +2. And notice when you write in set builder notation inside here, what are we talking about? Well, it looks just like the graph that we just made. We have a boundary on both sides with the 2. We know that greater numbers go to the right, so the open side of both inequality signs, where the alligator would eat, also goes to the right. And so in set builder notation, it looks just like our graph. So the second thing we're going to do is we're going to look at how we can decipher and get a word problem and use the words in the word problem to kind of come up with our inequality that's representative of this word problem. So let's read through. So we need to write this and graph this because we always want to make sure we answer the question and read the directions. So a movie ticket for a child younger than 13 costs $5.95. A movie ticket for an adult between the ages of 13 and 64 costs $8.95. And a ticket for a senior citizen, 65 and older, costs $5.95. Write in graph, so that's two things we have to do, an inequality that describes the ages of people whose tickets cost $5.95. Well, in words, we already know what's happening. There's only two sets of ages. One set is for the younger than 13 crowd, and one set is for the 65 or older crowd. These two sets don't overlap. these two sets are completely separate. And I couldn't make the statement that you could be younger than 13 and older than 65. That would not make sense. There's no time that you can be younger than 13 and older than 65. So the only way that I can be both younger than 13 or older than 65 is to use the word or. And so what this tells us in the problem when they say all the ages of people who are ticket holders that cost $5.95, this would be an or statement, because you have two separate things that are related by the main part of the problem. We're related by ticket priced. But what we're really looking at is two separate pieces that we're talking about together. So when we write that, this is really what we're saying, right? The problem states that a ticket for a child younger than 13, and a ticket for a senior citizen, 65 and older, costs $5.95. So those are the two groups that we just talked about. The next thing we're going to do is we're going to break down what the words mean. Age is less than 13, or age is greater than or equal to 65. Please notice that. A senior citizen starts at 65 and then bigger. 65 or greater than 65. Greater than or equal to 65. So it's both. So that's why this says greater than or equal to. So in order to be a senior citizen, you have to be at least 65. So the next thing we're going to do is we have to define our variable. Anytime we use word problems, we have to write down what we want the variable to be so that at the end we know what we're talking about. Let A be the age that will pay $5.95. Well, if A is the age that we're going to pay $5.95, some of that age has to be less than 13, or that age has to be greater than or equal to 65. And using those words, it's pretty clear what we're going to write. We're going to write that. And so when we write that, we've pretty much solved the problem. There's nothing else to do. The variable is by itself, and we have one simple statement of our compound statement, which is A, the age that you'll pay $5.95 for is less than 13, but not equal to 13. And then we have another simple statement, the other part of our compound statement, that the age A is greater than or equal to 65. So if I want to graph this, what I have to do is do exactly what we did before. I'm going to draw my line to graph this. I'm going to put down my two boundary points, or boundary numbers. I'm going to use what they tell me to write down what we're talking about. So we have 13, and that's an open circle. We have 65, and that's going to be a closed circle because it's or equal to. And now we have to think about a different type of way. And I like to think about this as what I call the Walking Dead way, or the zombie apocalypse way. You're on the inside here between 13 and 65, and you want to keep the things we're talking about outside. So where are the zombies? They're on the outside of these boundaries, and you want to be safe in the middle where no zombies live. So the first part, they're saying A is less than 13. Well, less than numbers go to the left, so that's that one. So that's what that looks like. The other one is greater than or equal to. Or we already have the or equal to because we have the colored in circle, so now we have to do the greater than. Greater than goes to the right. So we want to keep the zombies out. Okay, the zombies in this case are going to be the variable. If you don't like the zombie analogy, that's fine. So now we basically have this or statement. Remember, or statements have to have separate things happening. And the boundary numbers go where the dots are, and then the variable talks about all of the other numbers. Since it can vary, it changes, talks about all of the other numbers that it can possibly be. So since A would be out here above 65 and A would be down here below 13, there's going to be two pieces to this when we write in set builder notation our answer. So just like before, it kind of helps us out. We're using the same variable A such that, well, there's two things happening here. One thing is that A is less than 13, and now we actually have to write the word or, because there's nothing in this space here. There's nothing in this space here where you are safe from the zombies that are out here. Okay? You want to be safe from the zombies. So you want to be on the outs. You want to be inside the safe zone, and the zombies are what we're talking about. Okay? So it's saying two things. A is less than 13, or, because I have to put that or there, because they're not overlapping. They don't connect. They're not both true at the same time. They're true. One's true, or the other one is true. And we're going to have A on the other side. Now, I can write it one of two ways. I can write A is greater than or equal to 65, or I could have written that 65 was less than or equal to A. Either way works. It doesn't matter. I close with my fancy brackets. And again, this models what we've just graphed. There's the or part where you're safe and where the zombies are. Okay? You would not be safe. You want to be away from the zombies. Okay? So we're going to look at another one where it's not a word problem, but we're going to end up looking at a compound. And if you notice, this one's already telling us it's a compound right away because it already has an or in it. So we don't even have to figure out that it's going to be an or based on the words that we're told. It's already given to us that there's an or problem. So just like the and problem, we're going to split these up into two things. So 2a minus 1 is greater than 13, or minus 6a plus 11 is greater than or equal to minus 1. So I'm going to solve these separately, and then I'm going to use the knowledge that I've gained from the previous problem and the problem before that to graph them and write them in set builder notation. I'm going to solve each one. Again, I'm going to do what's happening with the variable and move away from that. So additive inverse again, I get 2a is greater than 14. I divide by 2, and I end up with 7 is greater than, a is greater than 7. Over here, again, additive inverse. These two cancel, so you get 6a is greater than or equal to minus 12. Now I'm going to divide both sides by minus 6, and now I have to remember when I divide by a negative, it's very important to remember that when you divide by a negative, my inequality symbol is going to flip. So I end up with a is less than or equal to positive 2. Doesn't matter if the number that we end up with is positive. The fact that we were dividing by a negative caused us to flip our inequality symbol. So now this is an or statement. So we can do it one of two ways. We can either graph it first, or we can write our set builder notation. So I'm going to write the set builder notation because I think I have it figured out. When I start, a is the variable I'm talking about, such that now here I'm going to actually switch these. Why? Because 2 is actually less than 7. And so since 2 is actually less than 7, I really want to put the a less than or equal to 2 on the left-hand side. Or a is greater than 7. Fancy brackets. Now, if you chose to do the graphing first, you'll see that it actually works out better for you. It makes it a little easier. You don't have to do this flip in here. It looks cleaner, and mathematically it makes more sense to have the 2 on the left and the 7 on the right, just to go in with our convention. When we try to graph this, we're back to where we were before. Our boundary is at 2. Our other boundary is at 7. So 2 is a closed circle because it's or equal to. 7 is an open circle. And so again, it says a is greater than 7. Greater than numbers go to the right. It says a is less than 2. Less than numbers go to the left. And so now you can actually see from the graph what it looks like and why your set builder notation actually is written in the correct way if you put the 2 on the left. Thank you guys, and I'll see you guys tomorrow.